Welcome to this presentation. I'm really excited to talk today about HTTP 2 because it's Spring 1 and we don't get a new version of HTTP every day. So we'll talk about HTTP 2 and how you can relate to HTTP 2 as a developer, DevOps, basically from the design of your infrastructure to deploying on your laptop. So we'll talk about many things during this presentation. I have a lot of content, and if you have a question, don't just raise your hand and we'll discuss. Just by a show of hands, raise your hand if you already watched the presentation about HTTP 2. Not many? Okay, right. Good, so you'll learn a lot of things. So my name is Brian. I'm working on the Spring Framework team. I'm working basically on the MVC stuff, web-related stuff on the framework, and I'm also working on the second application, which is the application that powers our own website, spring.io website. I really like everything that's web-related. I've also some background in networking and protocols, so when HTTP 2 came out, I was really excited. So if you want to have really an agenda for this presentation, we'll basically talk about how the main goal of HTTP 2 is to solve latency issues, but it's also introducing a lot of new features and a lot of new stuff that changes things. Even though it retains the semantics of HTTP 1, the verbs, status, etc., we still need to evolve and change a lot of things in our architecture and in our applications to really adapt to HTTP 2. I'll talk also about server push and stream prioritization, which are two of the most important features, new features of HTTP 2. And even though a lot of people talk about those like the perfect silver bullets, perfect solutions for many problems, we'll see that it's much more complex than that than we think. And we'll discuss how support is on its way, adoption is growing. We'll have HTTP 2 today, tomorrow, soon. But there are still many open questions about how to deploy and how to deal with HTTP 2 in production. So let's start. So quickly, I'll just go over that part because that's probably you probably know a lot more than me about this. So what was wrong with HTTP 2 with HTTP 1.1 in the first place? Not many things. We like it a lot. If you should know that the old RFC is now obsolete. There are new RFCs that are more or less the same one, but cut into pieces and improved in many ways. There are some parts that are made more clear right now in the RFC. But it also HTTP 1.1 improved a lot of things compared to 1.0, especially when it comes to persistent connections. Before we had to open a new TCP connection for every other request. That wasn't really optimal. But okay, HTTP 1.1 is here. It's not going to disappear soon, so we'll have to deal with this anyway for a long time. The biggest issues we can point to about HTTP 1.1 is probably sending and receiving a lot of redundant HTTP headers. That's not really efficient. Privacy is not here by default. It's a clear text by default, so that can be a problem. And also, if you're familiar with other protocols that you can negotiate on top of HTTP 1.1, like WebSockets, you know that it's not often really easy to go that route because when using HTTP 1.1 upgrade, because of a lot of software network appliances rely on port 80 being HTTP clear text, and that's it. Whenever you try to do something else on top of port 80, you run into issues. Basically, if you've tried to deploy WebSockets in production, you know that proxies and firewalls can block your traffic, and you have to basically use the secure version of WebSockets if you don't want to run into those issues. One of also the biggest issues with HTTP 1.1 is called head-of-line blocking. So head-of-line blocking is basically, we know that we can use the pipeline feature of HTTP 1.1. We can send many requests at the same time, but we also know that responses need to be sent in order. So we can't really have several responses at the same time. The order of requests is deciding on the order of responses, and that can be a problem. So it's basically first in, first out. So that problem you can see when you are opening your developer tools, and you see basically this. You see you're trying to load resources, and you're seeing that diagram, that kind of diagram. Usually what we do, we just open more TCP connections to a single domain to work around this, but it's often not working very well because we have a lot of resources. And we're also trying to have more domains, so domain sharding. But it has a cost. We already know about this. We're working on this already. So that's why we're also using other workarounds with HTTP 1.1. Some of them are just browser heuristics. Browsers tend to be clever, and they know that they should download this resource before than the other, and they're trying to do a lot of things clever to make the experience as best as possible. On the development side, we know that we're trying to concatenate files. Instead of having many JavaScript files, we're concatenating everything into one JS file. We're also using image sprites to have less files to download, basically. We're also inlining content. Same thing, less files, that's the end goal because of, again, head-of-line blocking. But if you look at the situation nowadays, that's a screenshot from the HTTP archive. Basically, you can see that modern pages, they tend to be bigger than 2 megs and to have more than 100 requests per page. So that's reality. We can't really work around this. We're trying with the domain sharding and many things, but that's reality. And again, we tend to have more or less 18 domains per page and 50 requests maximum per domain. So even if your application is not using those domains, you may include some tracking code or marketing library that does things for your users. Then that's where other domains can come in. So again, that's a problem we have to deal with today with HTTP 1.1. Also, another interesting thing about HTTP 1.1 is that whenever you're trying to improve the page load time of your application, you usually run into a big problem, which is nowadays, I mean, if you're trying to improve the page load time, if the client's connection is when it's getting better, like 2 or 3 megabytes per second, it's getting the experience is getting better. The page is loading better. But after 2 or 3 megs per second, it's not improving really much. Why? Because the latency. Latency is the main issue here. Experience shows that whenever you're decreasing latency, the page load time is decreasing. It's like linear. You can see it. So the main problem here with HTTP 1.1, whenever we're trying to concatenate more domains, a lot of things, the problem is here. The problem here is latency. And we know that user experience here is really important because if your application is not loading fast enough, then it can go from just noticing a slight delay or just checking another tab because you're a bit bored, or just closing the tab because you think that the page is not responsive. And this is getting worse because right now we are all accessing websites from our mobile device and often from not so great connections. So we have to deal again with this. So we've talked about those workarounds, and those workarounds, they can be problematic. We talked about domain sharding, adding more domains in your application. And the problem with domain sharding is that there's no real magic number. You can try many things, but in the end, like we saw with third-party scripts, you end up with a lot more domains than you think. So no magical number. And every time you're resolving a new domain, there's a cost for the DNS query, and that can be really slow. So when you're trying on your laptop or maybe in production, it's working pretty well. But whenever a client doesn't have a really fast DNS, it's really painful. And again, because we are trying to use many TCP connections, you're paying a price every time you're setting up a TCP connection. The handshake, the slow start, that can be really slow. So domain sharding may not be the answer. Same thing with concatenation. Whenever we are merging files into one, we are hurting the cache efficiency, and we are and cache invalidation is also really bad, because whenever we're trying to change something small into one file, the client has to re-download the whole concatenated file. So you're changing one bit, you have to re-download the whole thing. So it's not really efficient. Also client performance. Whenever you're trying to download one file, so it's better for, on the latency side, but for the client has to parse. If it's JavaScript, for example, the client has to parse the whole file, and that costs a lot on CPU and also latency. On the user experience. And it also tends to make our build more complex, because we are building our application on the client side with modules, module loaders maybe, and in the end we have to do a lot of things to just concatenate, and we try to do a lot of things to have a good experience in the end, but it's just trying, and sometimes it's not working really well. And Sprites, guilty. We have one on the Spring.io website. It looks like this. So the browser has to decode the whole file, even if you're just trying to display just one logo. And so again, CPU, memory, latency, you have to download everything. So less request, but it costs. And personally, I find it really hard to maintain. Whenever you have to change something, you have to deal with this. So it's not a really great experience, I'd say. So if we want to discuss the basics of HTTP2, HTTP2 is fixing latency. That's the main goal. And how? First, it's using a single TCP connection. It means we are spending less time within the TCP handshake. We're spending less time with TCP handshake and within the initial congestion window of TCP. And we're much better with our link, because we're trying to use our connection better. If our internet connection is good, then we're not trying to create a lot of TCP connections and negotiate and try to get the link at the full speed. If we're using just one TCP connection, we are getting the best experience we can get from our internet connection. And one other thing about a single TCP connection, HTTP2 is not only trying to make one TCP connection for communications between the client and server, but it's also trying to reduce the number of TCP connections overall. Meaning there's a feature in the protocol and in other places that can help you do connection coalescence. It means that whenever several domains end up on the same IP and the same SSL certificates, the client can reuse the same connection, the same TCP connection. So if you have a wildcard certificate and your subdomain.example.org and example.org resolve to the same IP, the same TCP connection will be used in the end. So that can be really helpful for latency. One other thing about HTTP2, it's using multiple streams. So within a single TCP connection, we have several streams. And a stream is basically, at most, one request and one response. So they're separated into multiple streams. And they're interleaved, meaning we can send several requests and receive several responses at the same time. We don't have the head-of-line blocking problem. The order is not really important here. So that we are solving the head-of-line blocking in a way with this. And all those streams, again, are within the same TCP connection. And we also have binary framing, meaning you can't really, even if you take out the encryption, you can't really look at the TCP packets with your eyes. You'll just have binary. So binary framing is changing a lot of things. So we basically have several types of frames within HTTP2: headers frames, data frames, and all of those are binary and well defined in the RFC. So you'll have to rely on your HTTP client to help you read that traffic, or DevTools, but you can't really use Telnet like before, or Netcat. It's impossible right now. So a short illustration, that's the kind of illustration we will use throughout the talk. Client, server, both arrows are actually one single TCP connection. The client can send frames, headers, data frames, different types of frame, same thing for the server. And here we are showing an example of request response. So the client is sending stream 3, basically headers, maybe a GET request on some URI. It's also sending another request, stream 5, so another request response mechanism. So with headers, and this time with data, so it's probably a post request with some body. And the server can answer with interleaved frames. So it can start answering with headers for the response of stream 3, some body, then maybe continue with the headers for response of stream 5, and continue with stream 3. So that's how it can happen at the link level. It's all interleaved, no real order, and we'll see how it really helps. One also really interesting feature of HTTP2, it's flow control. Flow control means the client and the server can negotiate at the beginning of a connection, and also any time during the connection. They can negotiate the frame size, the window size. They can basically renegotiate what kind of traffic they can expect from the other. So that can really help if the link, the internet connection is getting better, or if the server is pretty busy, the server can tell the client to not send too much, etc. So that's a way to really deal with the traffic in both ways, for the client and for the server. We also have HPAC. So HPAC is a whole spec in itself. That's a different RFC actually from HTTP2. And HPAC is solving the headers problem. So you can think of it as header compression, not having to resend all the time headers and receive them all the time. But it's actually a little bit more complex than that. Meaning on each end of the connection, the client and the server, they're maintaining header tables. And header tables, they are made of lines like this with an ID, a name, so it can be a header name. Here it's a path. The ones like path, like this one, they're a bit special, but we won't really talk about this. But anyway, you get an ID, a header name, and a value. And some of those lines, rows, are coming directly from the spec. So some of those are really static. You have to implement this if you're a browser vendor, for example. Some of those are dynamic, coming from the connection and what's happening on the connection itself. So for example, if you're sending some header that's defined already by the spec, so for example, if you're sending a path and /index.html header, this one is static and defined by the spec, and it's got a given ID that's defined by the spec. So if you want to send that header within the request, you just have to send the ID, and that's it. And if you're sending maybe some header with a value, a custom value, but the header name is known by the spec, then you can just send the ID and then the value, and that's it. And if it's completely custom, header name and value, you just send the whole thing. But next time you send this, you can just refer it by its ID. You don't have to send it again. And how does it work? Basically, the client and the server on each side of the connection, they have to maintain this header table. And there's an important thing to understand about this is that the order of frames is really important here. So if you're trying to implement an HTTP2 server or a client, you can't really just switch frames, the order of frames, because each table is actually representing state. Whenever a header is coming in or coming out, it's changing the state of the table to reflect what headers have been sent or received. And if the order is changed, then the states of the headers table can be desynchronized between the server and the client, and it won't work anymore. So that's a really important thing to get at the protocol level, but for us developers, you don't need to really pay attention to this. But it's a really neat spec, but it's separated from HTTP2, and that's a good thing because it's quite some pages. But still, if you understood that, you got the gist of HPAC. Last big feature of HTTP2 is TLS encryption. So if you read the RFC, you might think that it's not required because there is H2, so HTTP2 encrypted over TLS. There's also a variant which is called H2C, which is basically clear text. So the RFC is advertising both, but many vendors, especially browser vendors, Firefox and Chrome, they're not implementing the clear text version. So in many cases, you're better off sticking with the encrypted version. Also, H2C, the clear text version, is relying on HTTP 1.1 upgrade. So instead of, for the encrypted version, instead of relying on TLS negotiation and then running the protocol under TLS, for the clear text version, it's relying on upgrade, HTTP 1.1 upgrade, so same problem as WebSockets and all the other protocols that we discussed. So I know maybe you're thinking at that point, okay, my application is within my network and I'm pretty confident we can probably do clear text. But if you know what this picture is about, you probably know why maybe end-to-end encryption is a good idea anyway. So just really think about this. Maybe encryption, end-to-end encryption in some ways better anyway. So now, after this intro, we'll do some quick demo. Command. Yay, working. Okay. So we can take a look at, So I've got a project, which is a boot project, a simple boot project that I created using the start.spring.io website. I just clicked on web, and that's it. So I've got a project with a POM, SRC, man, etc. It's really just basic stuff. The thing I changed is, for example, one of the first things we can check is within the POM, I'm using the 1.3.0 M5. Boot 1.3 will come out really soon, but M5 is really great already. So we're using that version of boot, and we are using the web starter. We're using here Jetty. And we are also adding some more dependencies like HTTP2 server, Jetty ALPN. We'll talk about this. We're using some WebJars. And we can see a couple of weird things like this dependency. Why are we using this provided dependency? We'll talk about this a bit later. What is ALPN? We'll talk about this. We're using also an HTTP client to test things. And we have like those weird arguments for our Maven plugin. We're doing boot class path. Again, we'll talk about this, don't worry. If we try to run the application, so the application is running, and if we go on this, localhost and hello, name Brian, so it's working. We've got a hello, it's not insane. But the thing we can see right now is that we're using HTTPS, but the actual certificate is self-signed. So that can be a problem. You have to validate it every time. That's a problem during development. But because we have to use an encrypted version of HTTP2, we have to deal with certificates. Let me increase. No, it's not working. I guess you don't really see what's going here. Can I just? Okay, one thing you can do at first when you're dealing with HTTP2 is here in your DevTools, you can just click on the protocol and add the protocol column. That's how you see HTTP2 is working in your test application. The other thing is you can add a browser extension like this, which tells you that it's HTTP2. Whenever you go on this, it tells you HTTP2 enabled. And when you click on this, it's opening the net internal tab of Chrome. You can try to use this. Check the link here. Let me stop capture. Yeah, this. So if you're opening that tool, you can see the session between the client and the server, and you can really see what's going on at the protocol level. So that's if you don't want to. I mean, the kind of thing you could see at the network level, really at the TCP level in clear text, you can see here with those dev tools properly. So you can see that we're exchanging options when we're setting up the connection. We're sending headers. So that's a header frame here, a headers frame with the method path and some custom headers as well. And we can see that the server is sending headers as well here. We are receiving headers from the server with status 200. And after that, we're receiving data with the hello text. So this is really useful if you're trying to understand what's going on at the HTTP level. You have to basically use those tools. And you should know that developer tools on Firefox and Chrome, they are being improved as we speak. So you can see the protocol right now, but there are many HTTP2 features that are not really shown within developer tools, like HTTP push. You don't know when a response is actually pushed. So that'll probably show up. I think there's a bug in Chromium to display that status. So we have an HTTP2 application working. And if we check what's going on, it's just a simple controller. That's the hello part, so nothing fancy. And if we check the customizer, then that's where the HTTP2 configuration is coming. So right now it's a bit verbose. I think I can make it better for sure. So what we're doing here, basically, we are just getting what Spring Boot is configuring for us, for Jetty, automatically. And we are getting the SSL factory. So everything SSL related is configured for us by boot. And we are basically creating connectors, HTTP2 connectors here. So we are creating a connector for HTTP2 using ALPN for protocol negotiation. Again, we'll talk about this. And we are replacing the connectors that were previously created. Don't worry about all that code. I'll give you a link with everything, the whole code base. So now about SSL, because we talked about it. If you take a look at the properties we've set up, it's really simple. We've just used the SSL infrastructure of boot to set up things. So we are using a custom key store with a self-signed certificate for one application. So that you can create one with the tools provided by your JDK to create that certificate. Passwords, and we are enforcing TLS 1.2, which is a requirement for HTTP2. And with all this, we have an HTTP2 ready application. Yes, let me show you maybe one other thing. Not this. Yeah, the key store is here. That's the key store we've created. It's basically in our resources. I've put it there. And with all this, we can also maybe show a real integration test. So it works also very well. Basically, regular integration test, and we're using the OK HTTP client to test this. And we can see it can be a bit cumbersome because we have to get the key store and we have to create a specific context, SSL context, to add that key store to the client, because otherwise the client won't know. So you have to do that kind of things, or you have to add the self-signed certificate to your own laptop global environment, which I wouldn't really advise. So there are many things we can improve in that space. But if we execute that test, we can see that it works. It's just starting the server and oh no, sorry about this. Yeah, never mind. It was working. Anyway, we can go back to the presentation. Yeah. So one thing we have to know about this is that you can do things way more simpler because somebody we know and somebody which is in that room, I think, did basically the same thing with the HTTP2, undertow, and boot, and the configuration is like way more simpler. Instead of having to deal with connectors like I did, it's just enabling HTTP2 with undertow, and that works. So depending on the server and the implementation, that can be really, really different. But you can check out that repository and see that it can be really simple. Something else that I didn't show is that if you're trying to use tools like Wireshark to see things at the protocol level, you're basically stuck because it's all encrypted. So to do this, there are some ways to deal with this. So you basically have to start your browser with an environment variable that links to a file that will be created. And this file, whenever the browser is running, this file will contain this. And this is basically, the format is just a string client random plus the actual TLS client random plus the actual server client, the master secret. So with all that information, Wireshark and other tools that are compatible with this can decrypt the encrypted connection and help you with the protocol. And you can set, on recent versions of Wireshark, you have to go in preferences, SSL, and this log file, and you have to just set the log file here, and that will work. You'll have HTTP2 decrypted within Wireshark. So the browsers give you already a lot of tools, but that can be really handy, especially when you're trying to debug latency issues within your application. So now, support and adoption. So if you're trying to look at native implementations of HTTP2, there's already Apache Traffic Server, which is maintained by Yahoo, I think. Pretty good HTTP2 implementation. It's working pretty well. There's already an alpha patch for Nginx, so it's not in the main branch. You have to apply a patch, and it's still alpha. And it's also replacing the Speedy support. If you're using Speedy at the moment, if you're applying that patch, it's replacing the Speedy protocol. Again, it's also working. Big players are trying to test this right now, including CDN providers, etc. There's also a module for Apache HTTPD. There's also a new implementation of a new server, which is called H2O. A really interesting one. I really advise you to take a look at this because it's just implemented for HTTP2, and it's trying many interesting things and new features with HTTP2, with server push and prioritization. It's really innovative, and that's a really good thing to check out if you're interested in the protocol itself. Also, there's a library in HTTP2. So if you're trying to implement your own client or something like this, you can use that C library to have the protocol support for free. That's basically what curl is doing, the C binary. Curl is using that library. On the JVM, there are already some implementations out there. So undertow, Jetty, Netty, both client and servers. OKHTTP is supporting HTTP2 as a client, and Tomcat9 is working on this. It's working. I've seen what it's being done on Tomcat9. It's coming. So we've talked earlier during the demo about ALPN, and that's an important thing to really understand about HTTP2. So ALPN, it's allowing you to do protocol negotiation within TLS. So whenever you're starting an encrypted connection, so TLS, you have to know what kind of protocol you can talk to with the server. And ALPN is this. It's basically adding new headers, new metadata in the TLS handshake. And that way, the server and the client can negotiate which protocol they can talk together. So formerly it was NPN. So when it was Speedy, when Google was trying to do new things with Speedy, that was NPN. But with HTTP2, it's ALPN. So that mechanism, there's a spec. It's standardized. It's supported in many places. We'll see where. So that's how you negotiate the protocol. Whereas when you're trying to do this with H2C, the clear text version, that would be the equivalent with the upgrade mechanism, basically. The thing is, if you want to use ALPN, it's so deep into the TLS handshake, your TLS implementation must support it. And that's where we can see that that's more complex than we can think. Because basically, with HTTP2, you need TLS 1.2. So JDK6 is ruled out because it doesn't support 1.2, so not working. JDK7 and 8, they have TLS 1.2. JDK8 has it as a default. We have some hope here, but they don't support ALPN, so we have to do something. In JDK9, the upcoming JDK9, it will support ALPN. It's a work in progress right now. So that's where it'll be really supported in the JDK. An interesting note is that whenever you pick one version of the JDK, even for example 7 and 8, they both support TLS 1.2, but there are some changes of ciphers. So depending on the cipher you're looking at and you're planning to use, some JDK versions don't support them and some others do. So that's one thing to check. There's a link here if you want to check which ciphers are really used. So how do we support ALPN with 7 and 8? Basically, there's an implementation of this ALPN feature, and it's implemented in a jar. It's done by the Jetty community. And in that jar, you'll basically see classes that override some classes, internal classes of your JDK. Naming client handshaker and server handshaker. That's the part where you're dealing with the handshake, TLS handshake. So those classes need to override those native JDK classes, and to do that, you have to use the boot class path argument when you're starting your JVM with the prepend, the P for prepend, because those classes you're providing must be loaded before the JDK classes. If you don't do that, you're lost. You can't support ALPN and HTTP2 on the JDK 7 and 8. One more complex thing on top of that is that depending on, because the underlying implementation of the JDK changes with versions, the ALPN implementation, that jar, you have to pick the right version. So if you're using, I don't know, JDK8 update 60, you have to pick the right one, the right ALPN version for your jar. There's a link if you want to see the compatibility table. You have to really pick the right one. Hopefully, it will be solved with JDK9. with the ALPN support, Cypher updates, they'll do a bunch of things for HTTP2 clients, notifications for async support for body, server push, etc. And they'll use lambdas and completable future. Which leads us to Servlet 4. And in Servlet 4, we already know that with Servlet 3.1, we had some async I/O improvements. And with Servlet 4, we should have HTTP2 within our Servlet classes interfaces. So it will deal with the new features of HTTP2. It will work with HTTP2 as required. And they're also considering reactive streams. So if you were at the keynote last night, you had a glimpse of it. So they're discussing this because with the new async I/O model in Servlet 3.1, they really noticed that it's not really simple to go async with the old, I mean the programming model we've been having with Servlet until now. So they kind of worked around this, but it's really hard to, as a Servlet user, if you're working on Spring MVC, not working on top, but if you're, for example, implementing a web framework, you have to do a lot of complex things to really deal with async I/O, the new async I/O in 3.1. So to make things a bit easier, they are considering maybe reactive streams, which will be in some way in JDK9 in the form of concurrent flow. So that's scheduled for JDK9, and they're talking about this. So speaking about reactive streams, if you want to know more about this and really understand what it's all about, you can just stay in that room, 10:30. There'll be a really nice talk with Rossen and Stefan. They'll explain what is reactive streams and reactive programming and how it relates to non-blocking and threading and all this. It will make things way more clear. I urge you to go to that talk. It'll be great. And if you think about reactive streams, which is a way to control data between the client, the producer, and the consumer. So the consumer can tell the producer how much data it can consume. It's kind of more or less the same thing as flow control in HTTP2. So with reactive streams at the application level, at the API level, the consumer can tell the producer, I can consume X more items, you can send those items. So that's a way to control the flow of data. And it reminds you of HTTP2 flow control, actually. So HTTP2 flow control is basically whenever a client, for example, is sending data, the consumer here, the server, can tell the producer, okay, I'm updating your window, meaning I can consume XX more bytes. You can send me XX more bytes. So that way, if the receiving end of the connection is saying window update 0, it means it tells the producer don't send any more bytes. So that's a very good way to deal with probably slow clients, or if the server is overloaded, you can really control what's being received. And if the producer is sending data anyway, it's not allowed by the HTTP2 RFC, by the protocol itself. So that way you can really control at the protocol level the flow of data, and that really relates to reactive streams. So we've seen all those implementations, server implementations, and with this there are many things that can differ from one implementation to another, and that can really be good for competition. Because for a given server, if you look at its I/O and programming model, if it's an event loop or threading, so this is one way of choosing it. But also, you should look also at the optional features of HTTP2, the new features, server push and stream prioritization. We'll talk about this. Is it supported? You don't know, because you have to check this, because those are optional actually in the HTTP2 RFC. The server and client implementations don't have to support it. So that's one way to choose from one implementation to another. And also is the client or server proxy, supporting proxy. For example, is the server able to proxy HTTP2 to HTTP 1.1 or HTTP 2, HTTP 2? That can be really useful in your platform. So those are the things you should definitely check out when you're choosing your implementation for HTTP2, which kind of server you'll be using. Now about support on the client side for browsers. If you look at the Can I Use website, you'll basically see that IE, Edge now, Firefox, Chrome, they're okay with this. Safari, iOS, not yet, and Opera, Android, depends. But if you look at the market share, you can see that basically HTTP2 is already here. It's really well supported, almost 60%. And in maybe a couple of weeks or more, when iOS 9 and the next El Capitan release will come out for all Mac products, you can add 10% on top of this with iOS 9 combined with Macs. That'll be even more market share. Because yes, HTTP2 will be supported in iOS 9. So now if you look at the actual traffic, so those numbers are coming from official Mozilla numbers. So they're a bit biased because we are only considering here Mozilla for the stable version of Firefox. So if you're looking at those numbers, we're looking at all the responses that were received by Firefox browsers. You can see that 85% is HTTP 1.1, 14% is HTTP 2. And if you look at the actual total amount of traffic, basically half and half, clear text and SSL. So it means like globally, 25% of whole traffic is HTTP 2. So if we really want to, half of all SSL traffic is HTTP 2 already. So if we want today to improve that support, maybe it's not about browsers because the support is already out there. It's more about improving SSL support. So today what we can do is deploy SSL everywhere to prepare for HTTP 2 because that's the way adoption will grow. So thinking about this talk, I thought, okay, if you choose your implementation, HTTP 2, you get everything working, you should be able to deploy it. But then I thought there are really 6 steps you should really consider before even thinking about choosing an implementation and going with HTTP 2. There are things you should do before. One of them is checking out your TCP support in your platform. So it all depends if you're hosting your application on a cloud with a cloud vendor or if you're hosting it yourself. But there are really things you should do if you're hosting your application yourself. Basically, with Linux, with kernels, with 3.2 kernels, there are many things that have been improved with TCP. So I won't list all of them, but basically, before those versions, there were many inefficiencies in the way TCP is negotiated, in the way the slow start, the initial congestion window, so how the size of TCP packets is negotiated and growing during the connection. So those things have been improved. So right now, if you're using the defaults of recent kernels, the initial congestion window is using 10 network segments, so you're sending more data right from the start. As before, you were sending very little, and you had to wait to get to the full potential of your internet connection. There are also TCP fast open, which means sending data during the handshake itself to get even more, to get even better latency. And also an important one as well, which is proportional rate reduction. So whenever you're having a long-lived connection, like HTTP 2, if you're losing packets, previously it was basically retrying slow start. So you were punished really hard for those lost packets. And with proportional, with PRR, you're dropping a bit, but you're getting back to the full speed much faster. So that's also a really nice improvement. The good thing is it's really important for HTTP 2, but if you do that, it's also a really good thing for HTTP 1.1. You have to enforce also HTTP 1.1 best practices. So cache control and E-tag headers, gzip deflate, which is, by the way, not mandatory in HTTP 2, so you still have to use it. As well, image compression and media queries, so sending the right assets for the kind of client you'll have, if it's a mobile or a desktop. And get ready to remove all the workarounds we talked about for all those reasons. You also have to assess your infrastructure. because of those long-lived encrypted connections, it can be a real problem for your infrastructure. So is your infrastructure compatible with those long-lived connections, or will it just cut and close those connections if they're too long? What happens with load balancing and failover if something fails? Same thing for network devices and software. Is there something somewhere in your infrastructure that thinks that HTTP should be clear text and is relying on that fact and maybe checking traffic or doing some things? If you're using HTTP2 with binary and maybe encrypted, then it's changing a lot for those tools, including monitoring and metrics tools. So those are the things you should maybe think about right now, because once you're starting to deploy HTTP2, it's too late. Also, one thing you can do today is secure your application using TLS 1.2 and the right kind of certificates. So I think if you don't have a SHA-256 certificate with the right length of key, it's already a problem with your browser. So if it's not updated, I think the padlock in your browser address bar is showing like a warning if it's not already the case right now. So having the right kind of TLS, the right ciphers, and the right certificate, it already helps for HTTP2 adoption, because you'll be ready by then. One thing that will help for SSL and TLS adoption is let'sencrypt.org. I urge you to check out that website. So many companies are funding this as an effort to have TLS certificates for free or almost free, and that'll be a big game changer in CA authorities. So it will be. I think the first tests are coming in September or October. So I'm really excited about this. This should really help with TLS adoption. Also, now one thing we can also do is probably undo the HTTP 1.1 workarounds. So we know that most of those were harmful, and that they were not very good for HTTP 1.1, but we now know that for HTTP2 they're also very harmful, because we are hurting the whole model with one connection and all of this. One also big problem that we have to think about this right now is how will we support both 1.1 and HTTP2? Because those workarounds are good if you're using HTTP 1.1, because it makes the experience better. But if you want to support both, how will we support both? Do we need to have one optimized version of your application and another? We should see. Next step is we need to update our own development toolset. So we need to use the latest development tools, the latest Wireshark version with the keylog thing I showed you before. And another thing which is really helpful is that if you're testing your application locally, then you should use a new feature which is in Chrome Canary right now, and maybe in Firefox. So that feature is basically allowing you to throttle your own connection and simulate, for example, a 3G connection. And that's really important, because with HTTP2 locally, everything can look really smooth. But if you did something wrong, the performance can be worse than HTTP 1.1. So if you're testing with some latency, that'll show defects and maybe bugs that wouldn't show otherwise. So this is an important thing to use when you're developing. Now we'll talk about server push. Server push, that's a new feature of HTTP2. Again, it's optional, so it may not be there in the implementation you're using. And in my opinion, it's too often described as the go-to solution to really deal with latency and solve all of those problems, which I think it's way more complex than that. So HTTP2 push promises is basically working like this. So whenever the client is sending a request for a resource, here stream 5, the server can decide that the client will need another resource, like /other. And for this, the server can send a push promise in the main, in the stream 5, saying, I will send you another stream, which number would be 8, and I'll send you this resource. And after that, the server can just send the stream itself, the response itself, for that other resource, and can send as well the stream number 5. So that's a way to have several responses for one request. But actually, the server is sending the request itself, which is the push promise, so the get and the headers, and the content at the same time. So when the client will receive that, the client will either store that response in its cache, if the response is cacheable, or it will just store the content of that response in memory, short-lived memory. If it's not cacheable, it will store it anyway a bit. One thing that's important about a server push is that I've seen basically presentations suggest this. So server push is great. We are eliminating latency. We should basically push everything we can. So whenever we're downloading index.html, we should push all static resources. So all JS files or all CSS files, we should really push everything. And I don't really agree with that approach because that can be really problematic in many ways. Like, what happens if the resource is already cached? That works if the client cache is empty, but what happens if the resource is already cached in some way because you've been using cache control headers? So in that case, what happens is that the server will try to push resources like other and something, so pushing headers and pushing data. And the client, when the client receives that, the only thing the client can do is send reset stream headers saying, no, don't send this, I don't want this. I already have it, or I don't need this. So that may seem okay, but now think about it if you're sending like tens and tens of resources whenever you're loading a page. It's not really efficient just using your link just to send resources that are not really useful for the client, and the client has to use CPU to just say, no, 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 I don't want them. Another really important thing about push promise is that the spec is saying this. It's saying that if you don't send the frames in the right order, you can have race conditions. And the easiest way to understand this is that basically if the client is asking for index and so stream 5, the server is then responding with the stream 5, the page itself, the headers, and the content of the page. The client can then parse the page and see, oh, there's a CSS file here, I should ask for it. Then the client asks for stream 11 for the CSS file, and if the server is pushing that resource after it's already pushed started pushing the page itself, then there's a race condition because the client asked for something that the server is pushing right now. So it's really not efficient at all. So in that case, depending on time and many things, you don't know what will happen. Maybe the client will still get the full resource, or maybe reset the stream when the actual server responds again with the same resource on stream 11. So this is not really helpful. So the rule is, if you're pushing resources, you have to push those frames before you're sending the main resource. Otherwise, you may end up with that kind of race conditions. Meaning, if you're trying to push resources with some kind of servlet filter, you have to do this. You have to push resources, then deal with the main request. Otherwise, if you do something after the filter chain, then it may be too late and you may end up with race conditions. So it's really important to do this first. But you may think that if you do that, then you're delaying the main request. You're dealing with a lot of things, pushing things, before you're actually responding with what the client is asking, for example, the index.html file. So that can be hurtful. If you look at Jetty, at the Jetty implementation, Jetty, they have a filter, which is called a PushCacheFilter, which is basically doing something like this. They look at the requests coming in, so for example, index.html, And then they're looking at other requests coming in, for example, main.css, main.js, and they look at the refer header, and they see that those resources were asked within the context of the main page. So they're storing this into memory, and next time another client asks for index.html, they will preemptively push the CSS and JS files that were asked. So that can be clever because that's solving automatically latency. But there are some limits with this. For example, if you have one mobile device and then one desktop device, if you're probably not sending the same resources if you're using media queries. So not the same images, not the same resolution, not the same resources. So what happens with this filter if you're sending big resources to mobile devices when those clients don't need them? So there are some limits with this, I think. In a way, in a general way, is pushing everything really efficient? So should we push things only when the cache is empty on the client, or should we, what happens when those resources are already cached? How should we deal with this? Should we push only things that are necessary for the initial render of the page, the painting of the page, or should we push everything that's needed for the application to be ready to be used? So if we want to send just the right resources for the page to be painted, then we probably have to maintain the list of those resources manually. So we just want to push to this, and that. So it means that at the application level, we have to deal with all that metadata for each page. So that can be really complex to deal with. And in a way, aren't we just denying everything the browsers know very well today? Because they have heuristics. They know what they need first and what they already have. So if we are pushing everything, we're just saying to the browsers, you're stupid, we know better than you do. And it's not really the case, really. So what do we need? What kind of information do we need to really make that smart decision about pushing resources or not? There are some information we don't really have and we'll never have, like what's in the browser cache, what's its CPU, battery state, we don't know that. Same thing, browsers internals. I'm really looking into those things, but I barely understand how the painting cycles happen at the browser level, how they deal with resources and what's most important for them. So that's really complex. And what would be best, like if the client could tell us, I need this resource first and that one after, and this one is way better, more important than this one. If we had that information, that'll be way easier for us to deal with this. And it's actually called stream prioritization, and it's also in HTTP2. I'll explain that. It's also optional, and it's really, I think it can be really complex to implement, and that's why many implementations, server implementations, don't support this. But indeed, I think it's really important because HTTP2 is solving latency at the protocol level, but for performance and for user experience, this feature is really important. So how does it work? Basically, the client, whenever requesting a resource, is sending additional information. One is dependency, so meaning here we are asking for a resource, stream 11, and we're saying that stream, that resource depends on stream 8. So for example, main.css depends on index.html. And then we are putting a weight on that resource. So the client says, I want this resource with this priority, and this resource depends on that other one. So in theory, we end up with some kind of tree with a stream 0 root with no resource, actually, and with streams, and some streams depend on each other, and they have different weights. And that's the theory, and that's the kind of structure you can build with those header information. But in fact, at the client level, that's how browsers deal with this. So they have, for Firefox, for example, Firefox has fake streams, so some kind of grouping feature, fake streams that are never really sent or requested. So they have leader, other, background, and flowers. So leader has HTML, all the HTML resources, JS, CSS, So those are all those resources. They're under this stream, and they have the weight 200. Images, they're depending on the leader group, and they have a lower weight. And if you look at the, maybe not weight 1, I'm wondering. It looks a bit low. Anyway, there's another group which is called Other, and that's where you have all the XML, the AJAX requests, all JavaScript that are marked as async at the HTML level. And there's a last group which is Beacon Streams, and Beacon, that's an HTML5 feature. That's a way to declare, for example, you know, those Google Analytics, all the beacons for analytics features. That's here. And for Chrome, they haven't really implemented this properly right now. I think they're working on this right now because they're basically left with what they had with Speedy. So they don't have dependencies, they just have weights. So HTML, CSS scripts, so just weights. But the experience shows that if you really implement dependency at the client level and at the server level, the difference is amazing. The performance is really, really different. So if you deal with this properly, then performance is basically dealt with, maybe. So is this enough if we do this? If we just rely on the client and we don't push resources, could that be enough? So is there a way to, at the client level, at the browser level, maybe with a JavaScript API to tell this resource should have a higher priority? At that moment, no. There's no, to my knowledge, there's no RFC or draft or anything that suggests this, but that could be really useful. So we might think also, so if we have stream prioritization, maybe we can just forget about HTTP push, server push, and that's it. But not really, because server push is just the best way to eliminate completely latency. And if you look, I mean, if you talk to some of the expert group behind HTTP2, some of them are saying server push is basically replacing your use case when you were inlining content in your page. So when you were inlining content in your page, you were pushing the content whenever the client had it or not, because you knew it was that important that it had to come really fast to the client. So maybe that heuristic, that way of seeing things is a good thing. So if you know that you were about to inline the content in your HTML page in the first place, so HTTP push is probably a good way to deal with this. But this is only working for your own resources, the resources you're sending that are part of your application. So if you're using fonts, for example, that are hosted somewhere else, or other libraries, you can't really do something better about latency and performance. You're stuck with them, basically. You can't really do things at the protocol level. You're not serving those resources. Now, a quick demo to show you something. So the server is still running. So if we look at the better. So if we look at another page, here we've got like a regular HTML page with some images. Some of them are actually, let me show you this, slices. So they're one big image made of several. So it's just a trick to show you something. So at the network level, what we can see is that when you have the first resource, which is the HTML page here, let me refresh here. So when you get the document, all the resources, you see that they're starting to come at the same time. Before you had that head of blocking problem, right now it's coming at the same time. And if the server and clients both support the stream prioritization, like I told you, that's even better. You see that only the really important ones are coming first, and then the other ones are coming. Interleaved, but still, you see the priorities going in your timeline. One thing that you can also see is that, okay, we're sending static resources, images, And we have one resource here that came into less than like 3 milliseconds, really fast. And that resource is, no, that's not the one. Let me, that'll be resources. I did something wrong. Probably this. Network. Yeah, so this is, there's a resource that came into 1 millisecond, even better, and it's called talks. Talks.json. Talks.json, and it actually, it's a JSON document that's helping with this search feature. Like if you're looking for a talk with Rossen, you can see the talk from Rossen that's coming later today or tomorrow. So this document is basically one way of showing you that here we just see that it came really fast, and the best way to show you this, it's actually being pushed by the server. So if we look at net internals, capturing HTTP2, refreshing. Here we have a stream localhost. I'm stopping the capture. Let me show you. So we're sending response headers. Okay, here. Here we can see that the server sent a push promise frame to the client for this resource, talks.json, with the actual content. So at the server level, how we did this is within the client, within the controller here. Within the controller here, this is the page itself. We're using the native Jetty API. So we can do way better with maybe a filter or something like this, but I just wanted to show you that it's really simple. We're just getting the dispatcher from the request itself. We want to get a dispatcher for that resource, talks.json, and we are just pushing that request, and that's it. And you can see that I did this before I handled the actual response for my main page. Whenever I return the name, that's where I'm done with my handler, and that's where I'm starting to deal with the main response. So I did push before I sent the content. So it's not really hard to do this. And one other thing we can see is that within the index template, I did something like this. So because I'm using some font coming from Google, I added a specific attribute, which is pre-connect here. And you might think why I'm doing this. And because I know that this font is coming from somewhere else, and I'm using this font as part of the main.css file, I know that I'll need it. And here you'll see, since I'm not serving this resource, I can't really push that resource if I need to. So that's where we'll talk about this feature actually. How is it helping? So resources is basically a W3C draft. So it's not related with HTTP2, it's just related to HTML. And you can check all the details here. It's just a way of telling user agents what it should do, and just hints and advice on how it should fetch resources. So there are several ways of doing this. You can put links into your document saying you should DNS prefetch. So you should do the DNS query, or you should pre-connect. So query DNS plus the actual TCP handshake, or you should prefetch the whole resource already, or even pre-render the document. So that way you can tell the client things about how it should deal with the resources, even though you're not serving those resources yourself. So that's also a really good improvement when it comes to latency and user experience and page load time. You should know that you can do the same thing with the HTTP headers. So you can send those headers within your responses, and browsers will do something about it. About support now, it's supported like this, IE11, Edge, Firefox, Chrome. Again, in terms of So that was prefetch. So right now only prefetch is supported like this, and pre-render is supported like this. So DNS, I mean, only the DNS query or the pre-connect, it's not really working right now. So those are the two that are really supported right now by browsers. So that's one thing you can use. And you can actually compare this to the thing I told you about earlier in string prioritization. That's more or less related to async. So whenever you're setting the async or differ attribute within your document, you're telling the browser to maybe load this asynchronously and execute it as soon as possible, or maybe download it and execute it after the page is loaded. So that same thing, you can tell the client, these are not really a huge priority for your application. You can just load them later. So that's also a way to deal with the prioritization without dealing with that prioritization directly. You can just give hints to the clients.
If you have two async resources, two JavaScripts, will they be requested one after each other, or does it has any relation of the order of the JavaScript?
Yeah, the question is if you have several JavaScript, will they be executed in order? So if you're using async and defer, it's not the case. Right now, for regular applications, if you're using scripts, you should know that each script is loaded in order and executed in order. So it's blocking the page rendering. And if you're using those, it's not the case anymore. So if you're using this, you shouldn't have dependencies between your libraries. You shouldn't have one variable initialized in one script and used in another. Otherwise, because the order is not respected anymore with this.
Like if I have a jQuery and I have a jQuery, a script that depends on the jQuery, I should not use.
So with the jQuery example, you should load jQuery synchronously and maybe your modules asynchronously after, because you want to make sure that jQuery is before. Otherwise, if you're loading everything with defer, including jQuery, you can run into issues. Now, with your app into production, there are ways, I mean, what's the best way to deal with all this? In my opinion, right now, because it's evolving, I think we need to really consider carefully what kind of implementation we're choosing, which server which we are using. Is it supporting those optional features or not? How is it supporting? What is it doing? Because the behavior itself of those features, like push and especially prioritization, it's not well defined in the spec itself. It's defined what you can do and the format of a message that are exchanged, but it's not defined how the server should behave. And that's really one way server implementation vendors can do things. Are the browsers that are your clients, what are they supporting? Are they supporting resource hints or not? What kind of features are important for you, and what do you want to use, and et cetera, et cetera. So those are key elements you should really consider when you want to deal with HTTP2 and those new features. So far from just pushing everything like I heard in other talks. I think it's way more complex than that. So in production, we can also think about proxies, because we often have proxies in front of servers. So if you're using, for example, a CDN, one thing that CDN vendors could do is basically when the client is asking for a resource, if your server is responding with HTML and resource hints, like pre-connect, pre-fetch, the CDN proxy could be clever and could fetch that resource, and whenever a browser is requesting for this, it could push it. So because he knows that you are giving that hint. So CDN and proxies, there's a lot of interesting things going on here. It's not really defined how they'll play with this, but there are ways to use HTTP2 in clever ways. Same thing for CDNs and proxies. Maybe they'll be the solution to our HTTP 1.1 and HTTP2 migration problem, because we have to deal with them both at the same time. So you probably don't want to have your your application properly modularized, etc., and also concatenated files and all those workarounds you were using for HTTP 1.1. So if you're using just the proper version with no workaround, maybe that proxy can do something for you. It's already the case with the Speedy and tools like Google PageSpeed. So Google PageSpeed is concatenating and optimizing resources on the fly for you and inlining them. It's doing a lot of things. You can configure it if you have your own proxy, and if you're using a third party like a CDN vendor, it can be done for you. So here, cloud vendors, CDN vendors like Cloudflare and Akamai, they're working on this. So maybe that's a way to deal with that migration phase we are worried about. Another problem that is not yet decided upon is how do you package your application with that ALPN problem? You probably don't want to package your executable jar and then deal with an ALPN jar and push that to production. Or do you want to have all those snowflakes in production with specific scripts because you're using such JDK and ALPN and that? Or maybe you want repeatable staging and a way to reliably send your application to production. And if you do that in some way, you'll probably do something that Cloud Foundry build packs are doing because that's their job. And right now they're not dealing with ALPN, but maybe they'll do someday. Because that's a good thing to know. They know about which JDK will be set up in the Docker image when it's deploying the application. So maybe they can check the application and know which Jetty ALPN jar it should use or not. Another big problem in production is distributing secrets. So because you'll use certificates everywhere, if you're not using a CDN vendor to do that for you, you'll have to deal with certificates. And if you have a big app, you have to distribute those certificates. And how do you do that with a cloud native application? There are many ways to deal with this. Some of them are already supported. If you're using Spring Cloud config server, you can encrypt the keys and decrypt them only in applications using environment variables. But there are probably better ways coming, including in Spring Cloud with tools that are specific to managing secrets like HashiCorp Vault. So that tool is made for dealing with secrets and just giving them with a certain amount of time. And so those tools maybe will help us dealing with certificates without just copying and pasting everywhere in our repositories and in our infrastructure. One next thing about HTTP2 as well in production is that we can see that even big vendors like Apple are considering HTTP2 right now, because until now, if you were using the push notification service in your iOS application, you had to have your own server, send queries to the APNS, the notification service. And so I want to send this notification to that mobile device and send all those queries. And periodically, you had to pull another service to ask for feedback, and that feedback service would tell you those IDs, they have uninstalled your application, so you're wasting your time. You don't have to send notifications, they're gone. So until now, that's how this worked. And for the next version of their service, they're replacing HTTP 1.1 with HTTP 2 because you get that feedback for each response, for each notification push. And before, they had to do this because there was the head-of-line blocking problem. If you wanted to send a lot of notifications, you had to send a lot of requests. And if they were to send a response about this ID is gone or not, then they had to do it synchronously with the head-of-line blocking problem. So with HTTP2, they can send you the responses whenever they're available, and you don't have to deal with a separate service. So that's one big example of this. And if you think about microservices as well, HTTP2 may be even more ready for this use case than the traditional client server. So because in microservices, when you're talking from server to server with REST APIs, you need request response, REST JSON, you may be using RPC technologies. You want low latency and you want security as well. So it's all built in with HTTP2. So that's a really good use case. And you can even think about HTTP push in that context. Whenever you're sending HAL responses, if you're sending links, like we saw yesterday during the keynote, then you may say, there's this related resource you may want to check out. And if your API may be clever, you may want to push that resource already with the response, because you know the client will ask that response right after. So push notifications, I mean push responses can be really useful here. So that's everything I had. The code will be up here. The slides will be available shortly. So thanks for your attention, and enjoy Spring 1. And if you have questions and if you have some time left, I can take a couple of questions, or I think I'm out of time. I think it's 10. So thank you. Questions? Nope? Yeah, just one.
I've got a couple questions. I'll pick my favorite one.
Yeah.
During your pre-check, you may have addressed this, but during your pre-checklist phase, you talked about analyzing your infrastructure. But then at the beginning of the talk, you talked about how we fan out to like 20 different domains. So it figured out sort of infrastructure too. And are you suggesting that things like the proxy solutions and such, is that sort of a way of addressing the fact that you might be all HTTP2 ready, but 15 of your 20 domains you get resources from.
Okay. Yeah. So the question is, when I was talking about the pre-flight checklist, so is it should we take care of this even if we're hosting everything, or should we use maybe a proxy, a CDN proxy, to deal with this for us? Both choices are valid actually, because depending on the company you're working for and the kind of things you're doing, if you're hosting everything and that's your job, then you have to deal with the pre-flight checklist. If you're using Cloudflare or some vendor, CDN vendor, they'll deal with the certificates, with all those issues for you. I mean, most of them. So if you're cool with that, then that's one way of dealing with this. And they're already working on HTTP2 support. So yeah, that's a good way of dealing with this, for sure.
But you might also just be a solo programmer integrating with a bunch of services.
Yeah. Oh, in that case, yeah. If you're on your own and you're developing your application, then going with a CDN or using your cloud hosting environment, if you're using PWS, for example, the solutions that will come to Cloud Foundry about this, they'll probably help you with this in a way. Cool. Thanks.